Alright, so goal of this video is to prove a very important theorem related to continuity, and that is called the intermediate value theorem, or the IVT. Okay, so the statement of the theorem is what I have already put on the screen, namely that if you have a function f that is continuous on an interval I, remember in this case we are not restricting ourselves to open or closed intervals, right? I is any interval. So if you have a function f that is continuous on an interval I, then f satisfies the so-called intermediate value property. And what is this intermediate value property? If you pick any two elements a and b in the interval I, such that let's say a is less than b, and suppose that y lies between the function values at a and b, that is y lies between fa and fb. Right? Now what does it mean to say y lies between fa and fb? Either f of a is less than y, which is less than fb, or the other way around, right? F of b is less than y less than f of a. Right? So if y is intermediate between the function values at a and b, then there exists some x naught between a and b such that at x naught the function value is exactly equal to y. Right? So the way to read this is that if you take any two function values that are taken by the continuous function f, then any intermediate value between those two function values, which in this case is denoted by y, is also in fact attained by the function, and it is in fact attained between the points of attainment of the original levels. Right? So in other words, y is x naught, which is the point at which the function value y is attained, is in fact between a and b. So pictorially, you will see that this is in fact a fairly straightforward, it should seem like a fairly straightforward consequence of continuity. So let's just see how this would look like pictorially. Let's say this is x of x. Let us say our function looks like this. Okay, and just for illustration's sake, let us say that this point here is a, such that this level is f of a. Right? Again, for illustration's sake, let us say this level is b. This position is b, and therefore this level is f of b. Right? And y, let us say, is here. So it's a continuous function or an interval. A, B lie in this interval. Okay, so in this illustration, f of a is less than f of b. So y will be somewhere larger than f of a and something less than f of b. The point is that there will be some element x naught between a and b where the function value is exactly equal to y, which of course we know to be pictorially true, because we know that, well, in this case, y is actually attained at a bunch of points, right? For example, this is a possible point at which the function value y is attained. As you can see, there are in fact others, right? There is this point, there is also this point, right? So in this illustration there are three, but the intermediate value property tells you that there is at least going to be one, right? Which kind of makes sense, right? Because effectively what you're saying is that you are starting off at here, right, at f of a, and you want to basically, let's say, draw this curve all the way up to this point, which is at b comma f of b. The only way you could potentially draw a continuous curve that goes from this point to this point is if it intersects the level y at some point, right, in the middle. And that is exactly what the statement of the intermediate value theorem is. All right, so now let us go about looking at the proof of this. All right, so the way we are going to go about the proof is that we will actually give a constructive way of even arriving at this position x naught. Okay, before we get there, let me assume that f of b is greater than f of a, so that the proof is, well, for the same case that is consistent with the picture above. Right, so the opposite case is easy to, opposite case works analogously. Okay, so now here comes the construction itself. So I'm going to define the set S. Right? What is the set S? It is the set of all real numbers between a and b satisfying the property that the function value is less than y. Okay, so just define S to be all of those numbers between a and b such that the function value is strictly less than y, right? This set is clearly non-empty. Right? In particular, A is guaranteed to belong to this set, so we don't have to worry about the emptiness of this set. Okay. Now let, and in fact it's a subset of AB, so it's in fact also a bounded set. Right? So this is clearly non-empty and bounded. Okay. Now let X naught be the supremum of this set. This is now a non-empty bounded subset of the reals, so we know that a supremum exists, right? This is a real valued quantity. Let X naught be the supremum of S. So what we will show is the following. We will show that thanks to the continuity of the function value at this particular x naught will in fact be equal to y. Okay, so again I leave it for you to verify that x naught defined in this manner is guaranteed to in fact be between a and b. It's clearly greater than a, and it has to be less than b. So I leave that that check for you. What we will show is that x naught defined in this manner as the supremum of the set S is in fact the point that we are after. That is the point at which the function value y is going to be attained. Okay. So now let us go about seeing how that is. Now because x naught is the supremum of S, I can construct a sequence in S which actually converges to x naught. Right? So there exists a sequence xn in S such that xn converges to x naught. Okay. However, the fact that the elements of the sequence lie in S means that for all n, f of xn must be less than y. Right? And since xn converges to x naught, it follows that the limit as n goes to infinity of f of xn, which is equal to f of x naught by continuity, must also be less than or equal to y. Right? Because f of xn is a convergent sequence, every element of the sequence is less than y, so its limit must be less than equal to y. So that proves one side of the inequality. We have proved that f of x naught is less than or equal to y. Right? So you might want to keep this in mind. That's one side. Now we have to prove the other. The way we will prove the other is we will now construct a sequence which actually converges to x naught. Remember, in this illustration, this is x naught. Right? In fact, if I go back to this illustration, you will see that the set S is essentially composed of these three segments, or rather two segments. Right? So this is what S is, the union of these two. Right? So the supremum is in fact this point that I have marked as x naught. Right? What we have done so far is basically constructed a sequence Sn which actually converges to x naught from the left. Now what we are going to do is construct another sequence Tn which converges to x naught from the right. Okay, to prove the opposite inequality. So I would do it like this. Let Tn be defined as follows. It's the minimum of b comma x naught plus 1 by n. Okay. Now the first thing to note is that Tn of course belongs to the interval AB, but more importantly Tn in fact does not belong to S, right? Because Tn is going to be at least x naught plus 1 by n, right? Or it's guaranteed to be more than x naught, right? So Tn does not belong to S, which means that f of Tn is in fact going to be greater than or equal to y. Right? But by construction, because Tn has a gap from x0 which is at most 1 by n, we know that Tn converges to x0. Which implies that f of Tn, which converges to f of T0, sorry, f of x0, must also be greater than or equal to y. Right? And so we have essentially proved that f of x0 is less than equal to y and f of x0 is greater than or equal to y. We can conclude therefore that f of x0 is equal to y. Right? And that shows that the intermediate level y is necessarily attained by the continuous function f. Alright, so that is the statement and the proof of the intermediate value theorem. What we will now do for the remainder of this video is essentially go through a bunch of corollaries of the intermediate value property that we have just established. Okay, so the first of these is related to fixed points. Let me write the statement of that now. So consider a function f which maps the interval 0, 1 to 0, 1. In other words, it for values in the interval 0, comma 1, it takes values between 0 and 1. And suppose that this function is continuous. Right? The claim is that f has a fixed point. Right? Now, for those of you who may not know what a fixed point is, let me define. X is a fixed point of f if f of x is equal to x. Right? So fixed points of functions are basically those functions where the function maps that particular point to itself. Right? So such points, as the name suggests, are therefore called fixed points of a function. Okay, so we are saying that any continuous function from 0, 1 to 0, 1 is has a fixed point. Okay, pictorially, what does this look like? The illustration is of the form: this is x, this is f of x, let's say this is 0, 1 and 1. Now at a fixed point, f of x is equal to x, so a fixed point must necessarily lie on this line, right, the so-called 45 degrees line. The point here is that any continuous function over this interval 0, 1 must intersect this 0, 1 line. So you figure out any way of drawing this function f. Let's say this is f, then this is your fixed point. So again, you try drawing various profiles of f. It may be increasing, it may be decreasing, it may be oscillating, it can do any funny song and dance. But so long as it is continuous, the point is it has to cross this 45 degrees line. In other words, there has to necessarily be a fixed point. Okay, so that's the intuitive, shall we say, interpretation of the statement. The proof is actually a remarkably straightforward application of the intermediate value theorem. So what we are going to do here is basically define a new function g as follows: g of x is equal to f of x minus x. Okay, now g as constructed is such that basically any point where g is 0 is a fixed point of f. So the zeros of g, what are zeros of g? Points where g of x is equal to 0, right? So zeros of g are fixed points of f. Okay, so now how do I argue that there is necessarily a 0 of G? Okay, so first we say, the first thing we observe is that G of 0 is guaranteed to be let's see, f of 0 minus 0. So G of 0 is guaranteed to be greater than or equal to 0, right? Another thing to note is that G of 1 is guaranteed to be, well, less than equal to 0. Why is that? Because G of 1 is f of 1, which is between 0 and 1, minus 1, right? So G of 0 is greater than equal to 0, G of 1 is less than equal to 0. How do I argue that there is necessarily a 0, right? If G of 0 equals 0, then 0 is a fixed point. Similarly, if G of 1 is equal to 0, then 1 is a fixed point. Right? And finally, if neither of these two conditions is true, so if neither hold, what does it mean to say that neither hold? That that G of 0 is in fact strictly positive and G of 1 is strictly negative, then a 0 of G exists by the intermediate value theorem. And that completes the argument, right? So yeah, so the fact that the function is it's a continuous function, it is in the interval 0 1. The fact that it's non-negative at 0 and non-positive at 1 implies that there has to be at least one point where it is equal to 0, and that point where G is 0 is in fact the fixed point of f. Okay, so this is our first corollary of the intermediate value theorem. Now we will state a few more. Now the second corollary is that basically if you have any continuous function, it maps an interval to an interval. Okay, so if f is a continuous function on an interval I, then if you look at the image of this function over the interval I, in other words the range f of I, which is basically the set of function values taken over I, right? This f of I is also an interval, or is either an interval or a fixed point. Okay, so I mean you can think of, I mean I would think of a singleton point also as being an interval. Okay, so in that sense what this tells you is that if a continuous function necessarily maps intervals to intervals, right, which if you think about it should also be a fairly natural consequence of the intermediate value property, right? I've been using this term interval a few times, so let me just clarify in case it's not clear what an interval is. So I is an interval if it satisfies the following property. I is an interval of R if you pick any numbers, let's say a, b in I, and suppose that you can find a less than x less than b, then this x also belongs to I, right? So an interval is defined as a set such that if you pick any two elements of the set, then any element between those two also belongs to the set, right? Such sets are in fact called intervals. right? So the corollary then tells you that continuous functions map intervals to intervals, right? And as a trivial case, you can take singletons also as being intervals, right? So this is the first corollary. I leave the argument of this to you, right? It's in fact a trivial consequence of the intermediate value property. So the proof is an exercise. Okay, so this is the first corollary. Next, we will talk about inverses of functions, right? Specifically, inverses of strictly increasing functions, like strictly increasing continuous functions. So here is our, let me write that as a theorem. So let f be a continuous, strictly increasing function on an interval I. Okay, then we know that f of I, which is an interval, right? Let's call it J, is an interval by the previous corollary, right? Moreover, and f inverse, the inverse of this function, which maps well J to I, is continuous and strictly increasing. Okay, so what this theorem tells you is that if you have any continuous and strictly increasing function on an interval I, right, then we know that the image of the function is also an interval, right? So the inverse function clearly will map the latter interval J back to the interval I, right? And the claim here is that if you have an continuous strictly increasing function, its inverse is in fact also a continuous and strictly increasing function. Okay, I hope everybody is familiar with the inverse of a function. If f of x is equal to y, then f inverse y is equal to x, right? So yeah, so this is in fact the next statement. This also in fact follows from the intermediate value property. Okay, so most of the proof of this theorem is in fact going to be deferred to the following theorem, but yeah, let's make this argument nonetheless. It's easy to show that f inverse is strictly increasing. Okay, just apply the definition of what it means for a function to be strictly increasing to argue that if the inverse of a strictly increasing function exists, that inverse is also guaranteed to be strictly increasing. Okay, so that bit is straightforward. All you really need to show really is that f inverse is continuous, but the continuity of f inverse is actually going to follow from the next result. Right, so I'll break this proof here and just point out that the fact that it is strictly increasing is trivial. The continuity part which remains is actually, I'm going to defer that to the next theorem, which is interesting in its own right. Okay, so let me write that here. That is, let G be a strictly increasing function on some interval J okay. The claim is if the image of this function g of j is an interval, then G is continuous. Okay, so let's stare at this statement in its own right first and then worry about how it applies to the previous proof. If G is a strictly increasing function on some interval J, right, what the theorem says is that suppose that G of J, the image of G, right, over its domain, is also an interval, right? I told you what an interval is in a bit back. Then we can argue that G is continuous. Okay, if G be taken to be F inverse in the previous proof, then that basically proves the previous result, right? Because we know that F inverse is strictly increasing, right? And the domain of F inverse is an interval, which is J, right? What is the image? What is the range of F inverse? The range of F inverse is in fact I, which is also known to be an interval. So by this theorem, if the image of F inverse or G is an interval, then G is continuous. In other words, F inverse is continuous, right? So just take F inverse to be G in the statement of the next theorem and the previous theorem applies, right? This is actually by itself a fairly straightforward statement to be able to prove. So I'm comfortable leaving this as an exercise to you, right? So the idea is actually the intuition behind this result is that if G is a strictly increasing function, right, then if the image is an interval, right, what does it mean to say that the image is an interval? It means that the image satisfies the intermediate value property. Namely that if you pick any 2 points, then points between those 2 points in the image are also attained, right? So that's really what we are saying here, that when you say that the image of a function is an interval, we are saying that that function satisfies an intermediate value property, right? So here what we are saying is simply that if G is a strictly increasing function that satisfies the intermediate value property, then G has to be continuous, right? You cannot leave, if you are not leaving out points in the middle and if you're strictly increasing, then you also have to be continuous. Okay, so I leave the exercise to you. It is not difficult to prove this at all. What I will end is with a comment that this last theorem in fact provides some sort of a partial converse to the intermediate value theorem. Right? How is this? If one way of reading the intermediate value theorem is that continuous functions on intervals satisfy the intermediate value property, right? Namely that if you take any two elements in the range, then values between those 2 points are also guaranteed to be attained by the function. In other words, they also lie in the range, right? So continuous functions on intervals satisfy the intermediate value property. That's the intermediate value theorem. The converse here, why is it a partial converse? Because what we are saying is that if you have a strictly increasing function that satisfies the intermediate value property, right? The fact that the image is an interval is in fact saying that the function G satisfies the intermediate value property. So if you have a strictly increasing function that satisfies the intermediate value property, then that function is in fact continuous, right? So if you take additional structure, namely that it is strictly increasing, then satisfying the intermediate value property implies continuity, right? The IVT in fact proved an opposite implication. Okay, so I will stop here, perhaps except that I will state one more statement that is a consequence of the IVT, and rather than go through the proof myself, what I'm going to do is post the proof for you to be able to go through, on your own. So here is the statement. It also should make intuitive sense if you have understood the intermediate value property. Let f be a continuous and one-to-one function on an interval I. Right now it's continuous and one-to-one. Okay, In this case, what the theorem tells you is that the function is guaranteed to either be strictly increasing or strictly decreasing. Okay, so here you have continuity and you know that the function is one to one, right? Continuity on an interval of course implies that you satisfy the intermediate value property, but you have also said that it's one to one. The additional one to oneness according to this theorem implies that the function has to be strictly monotone. It has to either be strictly increasing or be strictly decreasing, right? Which makes intuitive sense because one to oneness implies that you cannot repeat a value, right? So if you are continuous and you can't repeat a value, then you have to either be strictly increasing or strictly decreasing, right? So I'm going to post the proof. Reading the proof is an exercise. Understanding the proof is an exercise. Right? This proof is in fact presented in the textbook Elementary Analysis by Kenneth Ross. So what I will do is I will post the proof of this result on Bodhi and I will have you as an exercise basically understand and internalize the proof. Alright, so that brings us to a conclusion of our discussion of the intermediate value theorem and its consequences.